In this presentation, we explore the pivotal role of Christiaan Huygens in shaping scientific history. We will examine how Huygens applied mathematical rigor to mechanics, successfully building a bridge between natural philosophy, probability, and the foundations of modern physics. Here we examine the 17th-century scientific chasm. On one side stood René Descartes' qualitative cosmos, a universe of swirling vortices offering grand theories, yet lacking mathematical rigor and empirical proof. On the other side was an urgent need for practical precision in astronomy, navigation, physics, and probability. This created the era's central unsolved problem: how to transition from simply observing that the universe moves to calculating exactly how it moves. Enter Christiaan Huygens, the architect of dynamics. Born in 1629 to a prominent Dutch family, Huygens moved beyond Descartes' speculative philosophy to pioneer a revolutionary framework. He combined geometric modeling, synthesizing Galilean mathematics with physical reality, with a strict reliance on direct mechanistic contact between bodies, rejecting action at a distance. Crucially, he brought uncompromising axiomatic rigor to the field, demanding that mathematical ideals align seamlessly with physical observation. Here we compare three giants of the 17th century: Descartes, Huygens, and Newton. Positioned as the critical bridge, Christiaan Huygens connected Descartes' speculative philosophy with Newton's empirical physics. While Descartes relied on deductive logic and swirling vortices, and Newton later introduced calculus and universal gravitation, Huygens advanced physics through geometric modeling, mechanistic contact, and harmonic motion. Proposing a groundbreaking wave theory of light based on spherical wavelets and pioneering the geometry of evolutes and involutes, Huygens provided the essential foundation that transitioned science into the modern era. To understand the cosmos, 17th-century science faced a grounded obstacle: the crisis of precision. Progress formed an interconnected cycle. Better astronomy required exact timekeeping, which enabled longitudinal navigation to fund further discovery. However, mechanical limitations created a severe barrier. Before 1656, timekeepers relied on verge and foliot escapements, losing up to 15 minutes daily due to friction and torque variations. Bound by the limits of gears, both astronomy and navigation stood stalled, awaiting a breakthrough.
In December 1656, Huygens patented the first pendulum clock, constructed by Salomon Coster, by overcoming a key oversight in Galileo's physics. Galileo believed a pendulum's period was strictly independent of its amplitude. However, that assumption only holds for tiny swings. In reality, a circular arc is non-isochronous, altering its timing as friction causes the swing to decay. To achieve true precision as a clock's mainspring winds down, Huygens realized the pendulum bob could no longer move along a simple circle, but required an entirely different mathematical path. To overcome the circular arc's flaws, Huygens turned to geometry. By introducing curved metal plates, or chops, at the suspension point, the pendulum string wrapped around them as it swung, steering the bob onto a cycloidal path. Huygens mathematically proved that a pendulum following this cycloid is perfectly isochronous, wide and narrow swings complete in the exact same time. Through this tautochrome curve, geometry effectively conquered the physical irregularities of timekeeping. Between 1650 and 1675, timekeeping underwent a monumental evolution. Before Huygens, crude verge and foliot mechanisms lost 15 minutes daily. Huygens' 1656 cycloidal pendulum harnessed gravitational harmonic oscillation, slashing daily errors to under a minute, though it remained unstable on rolling seas. Then, in January 1675, Huygens achieved another breakthrough, applying the mathematics of musical string vibrations to a spiral spring and balance wheel. By introducing elastic harmonic oscillation, he made timekeeping truly portable, creating the beating heart of the modern mechanical watch. To observe the cosmos, Huygens needed better vision. Working with his brother Constantin, he perfected lens grinding and invented the dual-lens Huygenian eyepiece, significantly reducing chromatic aberration. Superior optics led directly to breakthroughs in the heavens. In 1655, he discovered Saturn's largest moon, Titan, calculating its 16-day orbit. Then in 1659, Huygens solved a mystery that had baffled Galileo, revealing that Saturn was surrounded by a thin, flat ring nowhere touching the planet. Through optical engineering, Huygens dramatically expanded humanity's view of the universe. Huygens stands as history's first theoretical physicist, using mathematical formulae to define the laws of physics. In 1656, predating Newton, he formulated the laws of elastic collision and established the conservation of momentum. In 1659, his treatise De Centrifuga geometrically derived the formula for centrifugal force, force equals mass times velocity squared over radius. Crucially, combining this formula with Kepler's third law implied an inverse square relationship. Providing the exact mathematical foundation Isaac Newton later relied upon to formulate his universal law of gravity. In his 1690 Traité de la Lumière, Huygens directly challenged Newton's particle model by proposing the first mathematical wave theory of light. He posited that every point on a wavefront generates secondary spherical wavelets, forming a new wavefront along their tangent. Huygens used this principle to explain complex optics like birefringence and Iceland spar, distinguishing between ordinary and extraordinary light rays. Though initially overshadowed by Newton's influence, Huygens' wave principle earned ultimate vindication in 1818 when Augustin-Jean Fresnel adapted it to successfully explain light diffraction, cementing its place in physics.
Huygens did not have separate careers in horology, astronomy, and physics. He applied a single methodology to the entire cosmos. At the center of his work lies kinematics and harmonic motion. The exact same geometric principles governed his breakthroughs across timekeeping, wave optics, and mechanics, linking pendulum oscillations and balance springs directly to light propagation and elastic collisions. Ultimately, Huygens proved that the universe was not governed by qualitative, mysterious forces, but operated as a unified, measurable, clockwork system. In 1655, Parisian salons buzzed with rumors that Pascal and Fermat had solved the problem of points, a method for fairly dividing stakes in an interrupted game. Cut off from their private correspondence, a 26-year-old Christiaan Huygens set out to reconstruct the mathematics entirely from scratch. Rather than simply solving a localized gambling puzzle, Huygens created a universal system for valuing the unknown, laying a fundamental foundation for modern probability theory. Here we see a profound shift from fortune to framework in 1657. Before this turning point, chance was viewed as unpredictable fate. Risk was priced by gut feeling, interrupted games ended arbitrarily, and the core metric was simple hope. Post-1657, probability transformed into a quantifiable, mechanical system. By replacing intuition with strict mathematical calculations and introducing expected value, Huygens enabled proportionate equity based on future paths, turning blind superstition into an exact science. Here Huygens introduces the fair game postulate, establishing that the fair price for an uncertain outcome is its expected value. Expected value represents the exact cost of entry into a theoretically fair game, or justus lucis, replicating those exact odds. By placing payoffs A and B alongside their respective chances P and Q onto the scales of balance, Huygens established an absolute standard for rational decision-making. Nothing less is rational to accept, and nothing more is rational to pay. When a game is abandoned early, how do you fairly divide the pot? In Proposition 9, Huygens replaced guesswork with precision by systematically mapping every possible future state. By calculating expected values round by round, he constructed a recursive grid that solved the problem of points for any number of players or scores. This elegant mathematical solution laid the earliest groundwork for what we now know as dynamic programming. In the final problem of his treatise, Huygens looked beyond single games to explore survival over time, introducing the mechanics of gambler's ruin. He demonstrated that even in a perfectly fair game, a gambler with finite capital playing against an opponent with infinite resources, like the house, will eventually face total ruin. Beyond proving this inevitable collapse, Huygens provided the mathematical tools to calculate the expected duration of play before that inevitable descent into the abyss. What began in 1657 as a printed textbook to solve parlor games ultimately rewrote the modern world. Huygens soon carried expected value into demography, utilizing John Grundt's data to analyze life expectancy. In 1713, Jacob Bernoulli expanded on Huygens' foundation in ars conjectandi, formalizing the law of large numbers. Today, that same core logic powers modern index investing to value global market expectations. Ultimately, the portability of expectation evolved from simple games of chance into the backbone of modern finance, risk assessment, and global economics. What began in 1657 as a printed textbook to solve parlor games ultimately rewrote the modern world. Huygens soon carried expected value into demography, utilizing John Grundt's data to analyze life expectancy. In 1713, Jacob Bernoulli expanded on Huygens' foundation in ars conjectandi, formalizing the law of large numbers. Today, that same core logic powers modern index investing to value global market expectations. Ultimately, the portability of expectation evolved from simple games of chance into the backbone of modern finance, risk assessment, and global economics. Christiaan Huygens stands as the keystone of the scientific revolution. By synthesizing Galileo's mathematics with Descartes' view of nature, Huygens built the indispensable bridge to modern physics. Without his derivation of centripetal force, Newton could not have formulated universal gravitation. Without his pendulum, precision astronomy was impossible. Along the way he defined expected value. Ultimately, Huygens provided the blueprint that transformed the 17th-century cosmos from loose philosophical speculation into a precise, mathematical reality.